start, just briefly about me. My name is Justin Chau. I am on IHOT Robotics, so 1414. If you ever have questions or you want help with Gearbox Design, you can email me at that email up there. Also, feel free to ask any questions as we go along the presentation. So the topics we're going to cover today are the use cases of custom gearboxes. We're going to run through some examples. Then we're going to kind of generalize the design of a gearbox, and then we're going to talk about shaft retention and also modeling gears in the sketch level in terms of CAD. And we'll also talk briefly about motor curves and the characteristics of these brushed DC motors. And then lastly, after all of that, we're going to design a gearbox in SolidWorks. But if you have, like, if you're using Onshape or Inventor or whatever, feel free to follow along as well. So first, we're going to talk about the purpose of custom gearboxes. So when you want to design a gearbox, it's important to ask the question, like, does this particular application need a gearbox or a custom gearbox? Because if there's a cost alternative available from like Vex or WCP or AndyMark, something like that, there really isn't like a major benefit to designing your own custom gearbox. So you really only want to design a custom gearbox if you can have some sort of performance gain. So if whether it's like smaller packaging or it's reduced weight, or there's just like a particular feature of that application. And it's also important to understand your resources because like most teams have limited manufacturing resources, and you don't want to waste that in a custom gearbox if there is a cost alternative available. And along the same lines, COTS can sometimes be better than custom. And a good example of that is 4910 from last year. So for their gearboxes, they use a COTS gearbox called the Evo shifter for the elevator. And you guys, I think most of you remember how well they performed last year, so it's definitely possible to perform better with COTS than custom. One more thing to stress is use versaplanetaries because in terms of custom, it's difficult to beat the packaging of a versaplanetary for large reductions because it uses a planetary gear set. But there are some limitations to versaplanetary in which you would use a custom gearbox instead. For example, it's not great for large loads. Also, there isn't really an elegant solution for multiple motors to be used as input into versaplanetary. So now we're going to run through some custom gearbox examples. So we're going to talk about Cheesy Proof's gearbox from last year, some gearboxes from our team, and then some personal projects. So this is Cheesy Proof's 2018 Drivetrain Gearbox. So we can kind of break down the design into like a few key elements. So if you notice, like they're using 1/4-inch aluminum plate here. Also, they're using standoffs to keep the plates held together. And then the plate is also pocketed, and what that refers to is just the lightening patterns that you see in the gearbox to reduce weight. Also in their gearbox, they have kind of two sizes of standoffs. On the bottom, they have like kind of a larger standoff, and that's actually has a counterbore in the plate. That adds rigidity to the custom gearbox, but we actually didn't use any counterbores last year, and we found that was fine. And there's a benefit to not using that because in Georgia, we get access to water jets, and you can't do a counterbore on a water jet. So that's not necessarily, you don't necessarily need to use it, but it is an option. And then this particular gearbox is a shifting gearbox, so that they were able to achieve 2 speeds. And then also, it's important to consider why they designed this. It's kind of a unique design because it's much flatter than most 3-sim gearboxes. In this case, they use mini sims, but it's the same thing. And the way they achieve that is by, if you'll notice the mini sim here, is the pinion is connected to the first stage of the other 2 motors. And basically, it allows them to achieve this flat packaging. But typically, double loading the center pinion isn't really recommended just because it can break. But what they did to counteract that is they put a secondary plate here with a bearing to reduce the cantilever on the motor. So basically, they were able to achieve this flat packaging without reducing, I guess, the robustness of their gearbox. This is our gearbox from for our elevator from last year. So you'll notice that we designed our gearboxes in a very similar fashion to Cheesy Foods or other Californian teams. So we use pocketed quarter-inch aluminum plate again, and then we use standoffs to hold the gearbox plates together. And then the reason why we designed this gearbox is because for our elevator, we wanted the ability to shift between two speeds. And the reason for that is so we can place the cube faster, if you guys remember that game, and also climb with 3 robots. We never actually ended up doing that, but we wanted the capability to add that on. So this gearbox is designed to allow us to shift, so we can carry 3 robots with us, plus the factor of safety. Also, you'll notice how we still use versaplanetaries, right? So even though it's a custom gearbox, that doesn't mean you can use you can't use a versaplanetary as an input. The reason why we did this is just to have like modular gear ratios, so we could change the gear ratios easily, and also use the integrated encoder for the versaplanetary. This is just another gearbox. So again, it's pocketed quarter-inch aluminum plate, and then it's actually very similar to the gearbox we've been passing around. So basically what it is it's flatter than a typical 2-sim gearbox because we split the first stage. So the first stage is actually, you can see the gears here, it's split between the 2 sims, allowing us to like push the motors down. Also, you'll notice how it's also shifting. We have a pancake cylinder here to shift between 2 gears. And then this, we didn't actually build this, but it's a swerve module. And the reason why I wanted to show this is because you can use, I guess, what you learned from designing custom gearboxes in like many different applications. So while this isn't necessarily a gearbox per se, it uses many of the same principles as we'll learn when we're designing our gearbox in SolidWorks. Okay, so now we're gonna kind of break down what this style of custom gearbox is. So there are many different types, right? You can have sheet metal custom gearboxes, but we're gonna focus on this quarter-inch aluminum plate plus standoff construction just because it's easier to build in Georgia because we have access to all those water jets, right? So for the gearbox plates, breaking down what those actually do is they set the center distances between gears, right? So you have holes for bearings, and those bearings are spaced precisely such that the gears will mesh together. Then we also have motor mounting holes. Of course, you need to mount your motor to the plate. Then we have standoff mounting, and then also pocketing. So like I said before, that's like the lightning pattern you see on your plates. One note though, if you do pocketing, is you should really do that at the end of your design. So once you know your gearbox works and it functions, then you do the pocketing. The reasoning for that is because it's a huge time waster if you do the pocketing and then have to change your gearbox, right? Because the pattern or the pocketing pattern doesn't reflect your changes in your sketch easily, just because of how we're going to do it later. Then of course we have the standoffs that hold the plates together, and then of course your bearings, your gears, and shafts to the gearbox. So for our team, we particularly use quarter-inch 6061 T6 aluminum, and we do pocket. And then the standoffs we standardize using 1032. And the reason why we do that, or 1032 is a type of screw size if you don't know, but the reason why we do that is because Vex, WCP, and Handymark also use 1032 in a lot of their parts. So if you can standardize using 1032, you'll have a much easier time, like in terms of repairability. So the particular standoffs we use is a 3/8 OD2 from McMaster. So the part is listed here. You guys can go back in later and check it out if you want. But the reason why we use that is because it's easily drilled to 1032 clearance. It's also cheaper than the other alternatives. So there's also tube stock from Vex that's essentially does the exact same thing. It's a 3/8 inch OD tube with a .201 ID, which is 1032 clearance. So you can also use that if you just want to buy all your parts from Vex. You can also use Churro and Thunderhex to act as standoffs, but that's less common, and I wouldn't necessarily recommend that. For the shafts, we use Thunderhex shaft, and the reason why we do that is because, well, one of the reasons is because there's a through hole all the way through the shaft, and that's 0.201, so if you guys remember, that's 1032 clearance. But you can also tap that to 420. So if you have basically your shaft threaded, you can use a washer and a screw to retain your shaft in your gearbox. We'll describe that a little more later. And then also you can use half-inch hex gears. We also use 3/8 inch hex for our gearbox, and then you can use the Thunder hex variant. And that gives you the ability to tap to 1032, so you can do the same thing where you do a washer and a screw to retain your gearbox shaft. Really quickly, we'll go into some common gears in FRC. So you don't have to machine your own gears, like you can, but I wouldn't recommend that. That takes a long time. You can also source from McMaster, KHK Gears, all the standard gear websites. But Vex and WCP also offer a lot of gears that are, I guess, well suited for FRC use. So they stock 18 tooth to 84 tooth 20 DP gears, and also 20 tooth to 100 tooth 32 DP gears. And what DP is diametral pitch, and that's, we'll go into it later, but it's used in a lot of gear modeling equations, where it's the ratio between the number of teeth and the gear's diameter. So yeah. So for shaft retention, again, there are many ways to do this. This is the method I was describing earlier with the screw and the washer. So if you have a tapped like Thunder hex or something, you can put a screw and a washer there. Of course, you should use Loctite, but that would basically retain your shaft in your gearbox, right? You don't have to use like a lock collar anymore, so that's really nice. There are other ways to do it. So this is like basically if you turn down the two ends of your shaft and then you put it into the bearing, the hex kind of acts as like a shoulder, right? So it's kind of compressing the gearbox and it can't slide back and forth. And then lastly, you can use just a retaining ring or a clip, and that requires you just to machine a groove into your shaft, and then you can fit this on, and then it'll prevent the shaft from moving back and forth. So really quick about manufacturing custom gearbox. So CNC routers and water jets are really nice for this. And especially in Georgia, I would recommend water jetting because that can be outsourced and it's free to us. But you do have to purchase the 1/4 inch aluminum plate because it's not supplied like the 1/8 inch aluminum. One thing to know about water jets though is that they have taper. So as they, I guess, cut through the aluminum, it won't go perfectly straight down. So it'll kind of be tapered shaped. And most of the time that's fine, it'll still work. But you can also use a reamer to basically machine the hole just so it's perfectly the right size. Vex also offers like a reamer that they sell. It's slightly oversized for a 1/2 inch hex bearing, but it should look fine. And then they modified it to fit in a 1/2 inch shank, so that's like standard hand drill. You can finish off the holes with that. And then just like a few testing notes we did with the KSU water jet. So last year for the KSU water jet, we dimensioned all of our holes like the perfect or like the exact size as the bearing. So 1.125 and 0.875. And most of the time that did work for us, but we occasionally had to use a reamer to finish off those holes. And then so now this is a gear modeling equation. So remember the DP number we were talking about? So that's represented as P. And this is just the pitch circle of the gear. So pitch circle is where the teeth kind of, I guess, are meshing, essentially. So if we have a larger gear here and a smaller gear here, we have the outer diameter, which is where the ends of the teeth are. But then we also have where they interact, and that's your pitch circle. So your pitch circle is your number of teeth divided by the DP. So DP in FRC is normally 20 or 32. Now we have a center distance equation. So this basically is the equation you need to use to space your gears properly. So it's your total number of teeth on both gears divided by 2 times your DP. So again, 20 or 32 in FRC. You actually don't need to do this because in the previous, if you use this previous method, the circles are actually tangent to each other. So if you make them tangent, it sets your center distance automatically. But this is another way to do it if you don't want to use like tangency, or if you want to model your gear as the OD. So this is the OD equation, so it's the outer diameter of the gear. So it's very similar to your pitch circle, except that it's just n+2 divided by your dp. But then there is a FRC convention just to add 3 thou to your center distance, and that just helps for tolerancing. So yeah, so I would recommend if you use this equation that you just add 0.003 afterwards, or if you use this, you can actually model your diameter as 3 thou larger, and then when you make it tangent, because it's the radius, it ends up being 0.003 as well. So really quickly, a few motor characteristics. Yeah, so you have free speed, free current, stall torque, and stall current. And all of these are, basically they're all dependent on the motor being operated at 12 volts. So if you use a speed controller to reduce the voltage of the voltage input of the motor, all of these values can be scaled linearly down. So for example, if you operate at 6 volts, you can just multiply by half, and that will give you all your new motor specifications. And then really quickly about motor curves. So on the x-axis we have speed, and then we have all these different y-axes corresponding to the different lines. So a few key takeaways to this is that torque is proportional to current, and that's modeled by this equation, like T equals KT times I. And what that basically is saying that if you apply more torque, load torque to your motor, or like more load on your motor, then it'll draw more and more current until it hits your stall current and your stall torque. Also, as you do that, your speed is inversely proportional. So that means as you increase your load on the motor, it will also decrease speed. So I think you guys seen that at least like experimentally. And then one more thing is that motors tend to run more efficiently at higher speeds, so less load. And then when we're designing custom gearbox, you can use something called, or it's more of a guideline, but 8 to 10% of stall. So if you do that, there are a lot of benefits to this. One thing is like it's easier to control your control loops, or develop, make it easier to tune, because no one likes tuning PID. But also it's a key example of not using software to fix your mechanical problems. Also, in large productions, like normally have less efficiency, right? And that's in the form of friction, but we can actually use friction to help us in this case, because for an arm or an elevator, for example, your frictional force will oppose your gravitational force. So using a large reduction can actually basically make your arm stay in its position without even using a control loop, for example. And it's also much safer for its factor of safety if you have like different loads on your mechanism. Also, you're less likely to stall or burn out your motor. And then with that, we can see this locked rotor stall test. So basically, it shows how the motors perform over time when they're stalled at different voltages. So we can see this is for a 775 Pro. And if we use 2 volts or 4 volts, we're pretty much safe for the entire length of an FRC match if we stall. So, for example, last year we were using intake wheels, and with our 775 Pro, we would actually always rotate our the wheels just to keep the cube in place. And we were stalling out the motor, but that was fine technically because we were running at around 2 volts, and that's not going to cause your motor to burn out just because of this testing data. One last quick note about the breakers on your PDP. So when you're drawing current, it goes through a snap action breaker, and that's like the little rectangles you put into your PDP. But those are rated as specific current, but they won't actually trigger instantly. So let's say you reach 40 amps, it won't actually trigger until a few seconds later, and that's because they're activated thermally. So it takes a time for it to heat up and then trigger. So you can use this in certain cases just to draw more current if you need to. And then lastly, we can basically sum all of that up into using JVN. So if you guys know what JVN is, it's basically a calculator made by a mentor of Team 148. And it can be downloaded from Chau from this link here. And then you can do all these calculations by hand, but JVN just makes it quicker to iterate across your different gear ratios. And we'll actually be designing our custom gearbox based off these gear ratios given to us. So if you can see here, we're doing a linear mechanism, so you can imagine something like an elevator or something. Pulley diameter is this weird number because it's actually the diameter of the pitch circle of a sprocket, or the 12 to 35, number 35 sprocket. So if you have like a chain driving your elevator going up and down, you would use the pulley diameter as the same as your pitch circle of the sprocket. And then you'll notice here how we're drawing around 10% of stall. So that's aligns with our 8 to 10% guideline. So this is the gearbox we're gonna be CADing in SolidWorks. So if you guys have your laptops here, whether it has SolidWorks or not, it has Onshape or Inventor, you can pull it out now, and we'll start designing this. Really quickly, does anyone have any questions about anything I've discussed? I know I've been going pretty fast.
What were you using to shift the gears? Linear actuator or something, or?
So I'll show it right here. So we mainly use something called dog shifting for our gearboxes. And what that is basically you have a pneumatic pancake cylinder. So that's just using like air pressure essentially to push the cylinder back and forth, right?
Do you have to pause drive while you're shifting, or does it?
No. Like, you'll notice a bit of a break in your drive, but it's not anything super noticeable. So if you've seen that gearbox, actually, that piston is connected to a dog. So that dog has teeth on the side, and when it pushes back and forth, it engages the different gears essentially, and then that switches your gear ratio.
So it's always touching both at the same time?
Sorry?
It's always touching both sets at the same time?
Yeah, so it touches both sets of gear ratios at the same time, but the output gear is actually on the bearing, right?
Yep.
So they'll like freely rotate until the dog is pushed into the teeth on the gear. You can kind of see it on the output there. And did someone have a question back there? I think I saw a hand. Did you have a question?
It's just like an automatic transmission.
I guess. It's simpler, but yes. Okay. So now we're gonna start CADing our gearbox. So just one more time, this is gonna be our end product, hopefully. And so in your CAD program, you just start a new part. So if we remember like what the plate actually is, right? It's just setting the center distances between the bearings. So that's mainly what we're going to be doing, is just modeling the gears in a sketch, setting the center distances, and then making a plate with the basically with that basic geometry. So we start on the front plane, and then right now, like I like to start from the output essentially. So we have a circle just to model the bearing that's going to go into the plate. So this is the hole that the bearing is going to go into. And then for a 1/2 inch hex bearing, it's a 1.125 OD. Then what we can do is we can model another circle, and then on this bearing we have a gear, right? So this gear, if we look at the JVN calculation again, on our output gear we have a 72 teeth a gear. So that's what we're going to model here. So do you guys remember the equation for the pitch circle? I know I was going fast, but what was it?
It's like DG equals, I don't remember the one. I just know it was like something.
Or do you remember what DP is? Like, it's the ratio between, yeah, so the number of teeth and then your pitch diameter. So that's basically the equation, right? So we have, we have 72 teeth on this gear, and then we're gonna use a 20 DP gear, right? Because I didn't mention it earlier, but normally use higher DP gears for near the output stage. I guess the first stage or something can use like a 32 DP gear if you're going to use a 775 Pro. Because the pinion of the 775 Pro is 32 DP. So you can't mix and match the gears. So if you're using a 20 DP gear, you need to have an accompanying 20 DP gear. So the pitch circle of this gear is 72 divided by 20, and we're going to use plus 0.003 because tolerancing. So that's the gear, right? It's basically a circle representing the gear. So we can make a construction line because that's not actually going to be part of our final part. The next, the gear driving this is a 22 to 20 DP gear as well. So if you guys remember, it's 22 divided by 20 plus 0.003. And now this is the gear that's going to mesh with this gear, right? So we can set the center distances two different ways. One using just like a line and then dimensioning the line. But because we modeled these gears as the pitch circles, we can actually just make the two circles tangent. So now it kind of looks like a gear, right? This gear is just rotating and it's going to rotate this output gear. And then of course this gear needs a bearing. Because it's a smaller gear, we don't really need to use a full half-inch hex bearing. We can use a 3/8 inch hex bearing, and the OD of that is 7/8. So this hole and this hole is actually going to be part of our final plate. That's why it's basically highlighted in SolidWorks. It might not do that in Inventor or something, but yeah. Now we have another gear, right? So this gear is part of the first stage, and this is where the 775 Pros are going to be connected to. So if we dimension this, that is an 80 tooth gear, so we're going to do 80, but because it's connected to the 775 Pro, we need to do 32 DP. So it's 80 divided by 32 plus 0.003. And then because it's a gear, it's not actually part of the final part, we can make it construction geometry again. And then now we have, I should have clarified it before, but this gearbox is basically two 775 Pros as input, right? And then we're going to have an output here, and there's going to be a sprocket here, so you can imagine it being connected to the first stage of an elevator or something, right? The calculations are here. So now we have to model the pinions of the 775 Pro. So we have two 775 Pros, so we need two pinions. So they're going to be the same size, obviously, so we can make them equal. And then basically the pinion that Vex sells is a 12-tooth pinion, so we can do 12 divided by 32 plus 0.003. And then this is the output pinion of your 775 Pro. So you can make both of these tangent to the gear that it's driving. And we can also make a construction geometry again, because it's not part of the final part. Now we can actually, I guess, represent what the 775 Pro is going to look like in the gearbox by drawing two larger circles. And that's just helpful because you don't want to design your gearbox and realize like your motors are intersecting each other or something. So if you draw it in the sketch initially, you'll be able to plan everything out, and then hopefully if everything works out, you'll be able to just do it once and not like 5 times. So now with the 775 Pro, there's actually like a part that protrudes off the front, and that needs to go into the plate. So we're going to model that as well, because that's actually going to be a hole in the plate, right? So the 775 Pros can fit in. Those are equal. I think I already made these equal. Okay. And then for the outer diameter of a 775 Pro, it's 44.3 millimeters, but obviously you might not know that off the top of your head, and I had to look it up. It's on the Vex Pro website. So if you look, they have drawings for all their parts. So if you just look at the OD of the motor, you can model it. So that was 44.3 millimeters. And then here, the part that goes into the plate, the part that protrudes off the 775 Pro, I believe it's, let me double check. It's 17.8 millimeters. And then the motor is not part of the actual plate, of course, so we can make that construction geometry. This is not construction geometry because it's actually going to be a hole in the plate. One more thing we have to do for the 775 Pros is do basically the motor mounting. So the 775 Pro has two M4 screws that keep it connected to the gearbox. So we're going to model like basically a center or a midpoint line from both of the motors, and then we can set these equal. And then we have the two mounting screws for each of the motors. And then we can set all these equal as well because they're the same screw. Is everyone at this place who's following along? No? Okay. I think I'll give a little time to catch up to this point then, if you guys want. Is anyone actually following along or just watching? How's it going?
Going really fast.
Okay, I'm sorry. I'll slow down from here. But do you guys understand what we're doing, right? So in the sketch, you're modeling the gear as a circle, representing the gear as just a basic circle, and then you can show how the gears mesh together. And when you do that, it'll actually define all the bearing holes for you. Like it'll define where all your bearing holes should be. I guess I'll go to questions really quick while he catches up at least. Does anyone have questions about this? No? Okay. So we also need to dimension like the spacing between the two screws on the 775 Pro, and that is, I believe it's 29 millimeters. Oh yeah, it is. And then basically this gearbox, we need to find a way to mount it, right? Because you can't just have a free floating gearbox, it's not gonna help you. So a way you can do that is actually model, I guess, the outside of the gearbox. You can model like what it's connected to. So in a lot of FRC robots, you have 2x1, right? So we can attach this gearbox to a 2x1. And to plan out how we're going to mount it, we can actually just draw a rectangle that represents a 2x1. So a 2x1 is 2 inches tall. And then we're going to make this like centered on the gearbox. So this is just an arbitrary number, just like it's just long enough so we can model how we're gonna mount our gearbox. Okay, so now we have most of the basic geometry defined of our gearbox. One more thing is the screws on 775. Yeah, so 4 millimeters. Are you catched up yet? Right? Yeah, you are? Okay, nice. So now, basically, this is the basic geometry of the gearbox. The rest of it's gonna be like standoffs, like planning where you're gonna put your standoffs, also planning, basically making sure everything's gonna clear each other. Like I said earlier, we're gonna put a sprocket here because we're gonna drive an elevator or something, or it could be anything, it could be an arm. So we're going to model this as the diameter of the sprocket, which is 1.432 inches. And that's, again, if we look at JDN, that's the pulley diameter, because that's, your sprocket essentially acts as the pulley of the system. But we don't want this to be part of our actual gearbox. It's just there for us, so we're gonna make it constructed geometry. And now that all the, I guess, necessities of the gearbox are in place, we can start defining the shape of the gearbox. And that's not really, like, all of this was done just by like dimensioning. The shape isn't necessarily, it doesn't need to be one thing, right? You can form the shape around this basic construction. So, like, if you look here, like, all these seem to be like lining up, right? So we can just make it tangent to each other. And we're basically setting the outside shape of the gearbox now. So this is all the insides, but we need a fully closed contour for us to actually close off the gearbox and extrude the blade. So we're gonna do the same thing here. So we're starting to form the shape of the gearbox. It's starting to look like what we had in the render. But one thing we need to consider is how we're going to attach these two plates. Because if you look in the render, we have two plates that both have bearings, and they need to be connected to each other using standoffs, just to hold the plates together. And of course, those standoffs needs kind of holes for it to go through in the actual plate. So we're going to start modeling the standoff holes now. So we do 2 circles. And what this is basically the OD and the ID of the standoff. So the standoff OD can be construction because it's not actually part of the plate. And then if you guys remember, we use 3/8 inch standoffs. That can be any size, of course, if you choose to do something else. And the ID of the standoff is 1.196, and that's for basically 1032 clearance throughout the standoff. And then we can do the same thing, right? Because we can't just have one standoff holding our gearbox together. So you can just make it equal. And then make this construction geometry as well. And then for our robots, it'll obviously depend on how you do things, but we do a standard hole pattern on our tube, and it's basically just 1/2 inch from the side, and then we have a hole, and then another inch, and then we have a hole, and then 1/2 inch to the other side. So we have 2 holes running across our entire 2x1, and that makes it really nice just to move the positioning of things if we need to later on. So a really easy way to model that hole pattern is just by drawing 4 lines here. And then if you set all these lines equal, because we designed or dimensioned this line to be 2 inches. If we set all these equal, just divide 2 by 4. So that will set our hole pattern. So now this is 1/2 inch, and this is another 1/2 inch. So we can move these to be coincident with these points. And now it's set kind of like along the tube, right? And then for the tube, it's important to, I guess, like when you do a hole pattern, it's equally spaced across the side, and we want our gearbox to be mounted within the correct hole spacing. So what we want to do is dimension this to this. So that's our edge of the tube to the standoff position, or where we're going to mount our gearbox. And because we do a half inch, like a spacing between our holes, we want this to be like an increment of 0.5. So 5, I think we can do 5.5 here. So this is where our holes are going to be in the plate for us to put the standoffs through. And then we should probably put another standoff here, because right now all of our standoffs are on this side. So we do the same process again. And then this is construction geometry. And then this is also going to mount our hole pattern, right? So we want this to be horizontal to this point, so we can just do that, and then set it horizontal. So now this rides along R2 on our hole pattern. The same thing applies. We want the distance between the edge of the tube to the standoff to be increment of 0.5 if you're doing this type of hole pattern. So we're going to dimension this to here. And I think if we do 3.5, that looks about right. So this is, again, is arbitrary. It's not based off a calculation. It's just what you think looks right, or in terms of how you're going to assemble your gearbox. And then I think we can also do a standoff here and here. So same process again. And then for the standoff, just to place it, we can just make a tangent to the edge of our gearbox, which will be here for the plate. So we can do that. And again, this is up to you. You don't really need to make a tangent. You just need standoff somewhere in your gearbox. And then we're going to make this equal to this, because it's the same 3/8 inch standoff. Not equal to that, because it's the same ID. And then from here to here, we do the same thing. Are you about in this place?
Sort of.
Okay. So now we have most of this is basically every single hole that's going to be in our plate, right? So this is basically our gearbox design. All we need to do now is close off the plate to make it one closed contour, and then we can extrude it, and then it'll be our 1/4 inch plate. So this is kind of just like connecting the dots, essentially, connecting where all the outlines of your components are. So you can just use tangency to make straight lines across and form the shape of your gearbox. Do you guys understand what I'm doing right now? Like just closing off the shape? Yeah. And then for things like this, so like when it's blue in SolidWorks at least, or I think it's blue in Inventor as well, it just means that it's underdefined, right? So for this is all the possible positions you can put your motor at. And it doesn't really matter, right? Because we defined it being tangent to this circle. So any of these positions work in terms of meshing the gears. So we can just put an arbitrary dimension in there to just make sure the motor is fully defined in our sketch. So I'm just using a construction geometry line for us to dimension off of. And then I'm doing infinite length line across the center of our gearbox, just to give me like a place to dimension off of for angle. So you can dimension that to that. And then that looks about right, so I'll just make it a nice number, 72.5 or something. So now it's slowly becoming fully defined, right? As the lines turn black, you're getting closer to having the plate finished, and we can extrude it. Now I think let's close off the top somehow. So we can just do a straight line across. And then with this, like, it doesn't really matter for this gearbox because it's not going to be in contact with anything the gears aren't. But if you do something like a drivetrain gearbox, and let's say your wheel is here, and then you have your gear here, right? If you're doing an open design like this, where you just have the standoffs and the plates, you want your plate larger than your gear, just in case you like hit something on the ground. You don't want it to come in contact with your gear. You want it to come in contact with your plate. So you can see here like how I'm just cutting through the gear in terms of the plate. That's fine for this. But if you're doing a gearbox for a drivetrain, you might want to actually model your plate as larger than the actual gear, just so you don't hit the gear if you hit something on the floor. Are you in this place? And then here, this is kind of like, I'm doing it kind of sketchily, but what I'm doing is just closing off this corner here. And I'm doing just 3/8 just to keep the radius on the corners just constant. And then we can extend this line to hit this circle. And then we can do another one from here to here. So now we're kind of seeing the basic shape of our plate. It's similar to the one we saw in the render. We still need to close off this. And then we don't actually need it for this gearbox, but I'm going to show you, I guess, the standard for hole spacing for mounting your gearbox. So if you buy a gearbox from WCP or Vex, what they do is on the output shaft, they have a standard hole spacing that mounts to all their other stuff, right? So if you've seen like a Versa block or another type of bearing block from Vector WCP, if you do this hole pattern, it will allow you to mount your gearbox to that bearing block. So now if we dimension this line, their standard is 1.875, and they use 1032, like I mentioned before. And we can just make this equal to this because it's still 1032. And then we can drag this down. So that's a standard hole spacing for Vex and WCP parts if you want to, I guess, interface with the other COTS parts they offer. And then now everything is pretty much defined. We just need to position these standoffs. And again, it doesn't really matter where you put them. So you can just dimension it off something just so it's fully defined. You don't really want to leave it blue. So for this, that seems about right, and that's 1 and 1/16. And then we can dimension this to this standoff. and we can do something like 5 days. So now everything's fully defined, but we don't have a closed contour, right? So we still have the gap here, we still have the gap here. And SolidWorks won't extrude this until you close this contour. So we're gonna use this center arc and just basically close off these arcs. So we have a fully closed contour, and then we can extrude them. And then after this is done, what we'll do is we'll just extrude this to at 1/4 inch, and then that'll be our first gearbox plate. And then we can just put it in assembly, duplicate it, and then we basically have our gearbox plates done. Yeah, so now we have a fully closed contour. Are you at this bit? Yeah. Are-
It's not saying it's fully closed yet, not gonna lie.
Okay, yeah, mine isn't doing that either. Most of the time SolidWorks will actually highlight the fully closed contours, but if it doesn't do that, that doesn't necessarily mean it's not fully enclosed right now. I'm actually gonna go ahead and save this part. Let's stop for something. And then if we go to features and then we extrude this, it's starting to look a lot like what we saw in the render, right? So this is, once you reach this point and you know that everything clears perfectly, you pretty much designed the gearbox. This is the most important part of the gearbox. And once this is done, like all you have to do is assemble the gearbox in an assembly in CAD. So if we look here, so that's that plate done, right? So this plate is the exact same plate. You can sometimes see custom gearboxes where they have 2 different types of plates, just because you can save weight. Because on the second plate, we don't necessarily need this motor mounting holes, right? Because there isn't a motor going there. But it's just nice to keep the plate the same, just because when you manufacture it, you can just have one part rather than 2 different parts to keep track of. And then that's mainly the gearbox, right? All we have to add are the standoffs and then the gears. And the gears, you can just download off Vex. And once we place them in, everything will be done.
How do you design the cutouts for the weight reduction?
Yeah, so basically, I'll go into that later, but
Okay.
what it is you define everything you want to keep. So that's the principle. You define, so I'll go back to this plate. So with this, actually I guess I'll go ahead and do it now. Since we know this gearbox is gonna, like I CAD'd it before, so I know that it clears everything fine. Of course, you would do this at the end if you were CADing your own. Are you at this? Say yeah.
It still won't let me extrude for some reason.
Okay, it might just be like a few points that are off.
Yeah, it's probably
You just have to just drag them around and like close it off. But how you do the pocketing in the gearbox is you define everything you want to keep. So we obviously need the outer edge, right? We need something to hold the shape. So what we're gonna do is we're gonna offset the outer edge and then you can just reverse this. And then you can kind of see like the shape, right? That's the material we're gonna keep eventually. So a good number for that is just 1/4 inch as well. That keeps it safe. You can do less, but obviously then you might risk, I guess, like how robust your gearbox is. And then now we need this hole, right? And in order to have this hole, we need material around the hole. So we're gonna draw another circle here. And then you kind of see how this is similar to our picture here. So what I just drew is this outer circle that we're gonna keep. And that's basically how you do pocketing, is you just say, I wanna keep this, so I'm gonna draw material around it to keep. And then, so we're gonna have to do that for all our holes. And then there's a really weird glitch with SolidWorks where if you do all this pocketing, like where you define the material in advance, and then you do the I guess offset entities, it'll actually get rid of the center points of these circles, and it's really weird. So I would recommend, if you're using SolidWorks, just do the offset entities first, and then you can come back in and define all the material you want to keep. So I'm not dimensioning anything yet. I'm just like basically just making circles on all these points, and then we'll go back in and then we'll set it to size, like basically tell it how much of the material we want to keep. And then after that, we extrude all the empty space, and that forms the pocket. And then I think you guys can start to see why you shouldn't really do this before your gearbox is done. It's really time consuming. So once you make sure your gearbox does work, then you can come back in and do this for your final part. So now we have all the holes, right? So we want material around all of these. So we're gonna just make them all equal. And then we're gonna, like, you can just make this tangent to this, because we did model the standoff earlier, right? Or co-radial. So that defines this material. And if you notice here, we're gonna keep this material here, this outline, for this hole. And that's similar to what we have here, where we just have, I think you can start to see like how this is going to turn into the render. And then after we define all the holes, what we're going to do is basically connect them up. We're just going to draw lines to all the holes, and then we're going to offset them. Once we do that, it'll kind of form struts between all the bearing holes, and then when we extrude through this material, then it'll only leave what we need left. So I'm going to just go in and define this. I think 1.5 seems good. 1.5 here seems good as well. And this obviously can change. You can choose how much material you want to keep. And then I'm going to do this, and this, set them equal. And then set all of this equal as well. For this, I think 1 inch should work. So we're gonna keep material all around this, right? But then if we cut extrude now, then these are just gonna be free floating. So this is where we use just construction geometry to connect this up. So we're gonna draw a line here to here, right? And then that's eventually will use offset entities, and it'll kind of expand the line. And again, this is kind of just up to you, what you think will look most robust. Of course, there are like ways to analyze it, but when you're using 1/4" plate and the time span of like FRC is not really that worth it to do all that analysis, just because 1/4" plate is typically not gonna bend. So you can kind of see this web shape forming now. And we're almost done. And when I was CADing this gearbox the first time, like, it took time to like iterate and see what I wanted to do in terms of the pocketing. I just know where I like it now, so that's why I'm just doing it quickly. But normally we go back in and change things around to see what you think will work best. So now that we have all these lines defined, connecting all of our holes together, we can basically, oh, actually I'm missing one thing. So now we can just select all these lines. And then we can use this offset entities tool. And then if we do bidirectional, and then set this equal to 1/8 of an inch, this is kind of, oh, I missed one right there. This is kind of the same shape we had before. And then we click OK. Now eventually what we'll do is, you see this is a close contour where these struts meet these, I guess like the material for the bearing. And then we can just extrude cut through this and it'll form the same, or a similar pocketing shape to what we had before. One thing to note though is that it only does it, like with SolidWorks at least, you need to extend these lines to hit the edges. Otherwise, this isn't a close contour, right? So if you use this tool up here, and then we go to extend, we can click this line and you see it automatically extends it to the edge. And now this is a close contour for us to cut extrude through. And then that typically happens when it's not a straight edge because it does it correctly here. So let's just check to make sure all of that is correct. Yeah, so it's looking okay. So now if we go to features, we can do cut extrude, and then we can select all of our contours, right? So if I select that, and all of our close contours. And then you'll notice how like, we can technically select this as well, but that's kind of pointless. You're not gonna save much weight by doing that. And it's just, it gets really messy once you have to fill out all of these. So.
What kind of yield are you getting, like 30% savings?
Yeah, around. I don't know the exact number off the top of my head. So if we do through all, oh, okay, so this is very similar to what we had in our render. The only difference is we obviously have to go in and put fillets in all these corners. And obviously you need to, if you're doing something not water jet based, then you need to account for your tool diameter too. So with the fillets, obviously if you're using 1/8 inch and mil or something, then you need to make your fillets such that the tool can actually fit in. You don't want to crash your tool into the corner. So we're gonna do fillets, and this is again why pocketing is really time consuming. You just have to go in and click all these. You can use, in SolidWorks, you can use these features to kind of like auto select for you. But the issue, I guess the issue you run into is, for example, with this, SolidWorks will automatically try to fillet this and this, but it won't be able to do it because they're too close to each other. So in cases like that, what you have to do is you have to go in here, and then you have to use a face fillet. And then if you select these two faces, then it'll do your fillet for you. Otherwise, it won't work. So if we go in, so with the normal fillet, we can show you, like, if you click this, and then you click this, then SolidWorks will automatically fill it in for you. And this particular part of the pocket, it works great, right? Because none of the fillets are gonna crash each other, so it works fine, and you can just continue on to the next one. And so what I normally do is, I just do this, and I do one pocket at a time just to make sure nothing crashes. And then you can see for this, it looks correct, but it actually isn't. They're crashing into each other, so we can just deselect these, and then we'll use a face fillet later to go in and fillet that. We can click that, and then we'll do this, and it'll automatically fill in this pocket. That all looks fine. And then here, you have that issue where, you see, you don't really want that on your fillet, so you're gonna have to face fillet it later. You can also fix this in the sketch level, but that's just really time consuming. So I just go ahead and do this, even though it's technically not as good practice since you have so many features in your part, but. You can see up here again, we have the problem where the two fillets intersect. So you have to deselect it and then face fillet it later. Do this one. Deselect these. So you can imagine that if you do this, you spend all your time doing all these fillets, and then realize you have to change your mounting, or change where your gear ratio. That's not going to be fun to redo all of this. So, like, this is the exception where I know this is going to work, but otherwise, definitely do it and check your gearbox works with just like the flat plate, and then you can come back in and do this later.
Well, plus if you don't cut out the surplus, then you can potentially reuse a piece depending on.
Oh yeah, I guess so.
Possibly, yeah.
And then also, if you want to prototype and if you test these parts, you don't want to be waiting to machine all of these, right? The plate itself doesn't take long on a water jet, but when you add all these contours in, it does take much longer.
How long does this take on a water jet in your experience?
I know for last year's robot, I don't know if you guys remember how many gearboxes we had, but it took many hours. Like, I think it was like 20 to cut it, but we did have excessive use of the water jet. Like our belly pad, for example, was like the diamond pattern. That took a while, but I guess if you're prototyping one at a time, this doesn't take long, but it's when you add all of your parts together that the pocketing really does add up in terms of how much time it uses. So I think we did all the fillets that we could without using the face fillet, so now we have to use the face fillet and come back in, just select the two faces, and then it'll automatically do your fillet. So we're almost done with this plate. So that looks about right now. We can save that. And this is our finished gearbox plate and it's pocketed. So now we can go to an assembly. And then at this point, your gearbox comes together really quickly because this plate is the most time-consuming part of designing a gearbox. Otherwise, when you're just catting it, it's just a bunch of mates, just putting your motors together, putting the gears in, the bearings. So it's not that time-consuming afterwards. This plate is basically all you have to design, besides like standoffs, which is just like the cylinder you extrude. So what I'm doing now is just making sure the plates are, I guess, mated together correctly. So I just selected two circles, mated them. And now, basically all of our gears are gonna go in here, and then we'll be done. So I know you're the only one following, but if you get to this point, the folder I sent you guys has all the parts needed for this particular gearbox. But what we do on our team is we use a design library. So if you're using SolidWorks or like Onshape or something, you can get a design library set up. And then after that, you don't have to download all your parts again. You can just like go in here. So for example, for this, I made this folder for this session. But I can just pull in the part. And I don't have to download and convert the step. So that's nice.
Can't you download from McMaster as well, like some of the bearings and stuff like that? Or?
Yeah, so you can download from McMaster, Vex, WCP, AndyMark, all of those places. And then if you set up a folder on your laptop or computer, and then like I guess kind of configure SolidWorks to look up that folder, then you can just pull in the parts, and it's super quick. Like a lot of time, like before I did this, like I had to like go to McMaster, like find the part, download it, convert it to SolidWorks weight, and then like pull it in. So by just like having all of these parts here and then just pulling it in, like it's much quicker. And if you don't have one set up already, Spectrum, I forgot their team number, but Spectrum has a parts library that's designed for FRC, and it's really nice. This is what this is based off of. So most of this is just Spectrum's library. So if you look here, like if you go gears, they have like Vex 32 DP gears. They have all these gears. Like I haven't even used all these parts before, and the second I need it, I can pull it in. Like for example, this random gear, I can pull it in instantly. So for these bearings, if you guys remember, one way you can, I guess, constrain the shaft within the gearbox is by facing the flange of the bearings together. And then what you can do is you can turn down the shaft on either end. You'll notice how this is a round bearing, even though we're going to use a hex shaft, and the hex will actually act as the shoulder, right? So if you have standoffs going between the plates, and then your hex shaft has, I guess, is pressed against each one of these bearings, it won't be able to fall out. So that's a really nice way to hold your shaft together. if you don't want to use like lock collars or something, or even just like a screw and washer. And then now, because we have this design library, we can just pull in a 775 Pro, actually 2 of them. And remember how we designed this plate? This is where the motor fits in, and we put this hole in because this motor has this kind of protrusion out the front. So now if we make this concentric to this hole,
Why did you choose the 775 Pro for this gearbox? Is this a driving gearbox or is this like
no.
some sort of metal?
Yeah, so I wouldn't recommend using 775 Pro for drivetrain, but like for your mechanisms, in my opinion, the 775 Pro is hard to beat. For drivetrain, I would use like sim just to be on the safe side, or like, I know a lot of people are like pushing mini sim just because of its efficiency, but I don't, in my opinion, like I wouldn't do that at the moment. But yeah, so definitely for drivetrain, I want to run a gearbox like this, just because the 775 Pro can, I guess, burn out easily if you're trying to like play defense or something.
And then do you do CAD-based analysis to like try and estimate the forces and then the strength of your gearbox, or do you just have a prototyping-based approach where you just kind of make it and then test it with the mechanism and hope it doesn't explode?
So we normally just do prototyping just because when you do quarter-inch aluminum plate in FRC, it's, for the most part, like unless you're like on an edge case or something, it's gonna hold up fine as long as your pocketing is like reasonable. So we don't do CAD-based analysis, but I guess if you have the resources in terms of like number of team members to do that, like you could. We're a small team, so we don't do that. So this is the pinion I was talking about, and you can buy this on Dex or WCP. Actually, also ending right now. And actually, if you're on SolidWorks, I'm gonna delete this and show you a really, I guess, neat trick. So if you search copy with mates, and then you select your component, it'll actually have all your mates ready for you, and you just click where you want it, and then that's that pinion place. So if you have really complex components, and I guess you need to duplicate them, copy with mates is, I guess, a really nice way to do it. Now we have our 82 gear. So you can see, because we did that initial sketch and we modeled the gears as this pitch circle, now that we put this gear in, it meshes, I guess, like perfectly with this other gear.
And that's with the 3-valve tolerance?
Yeah. That's not something like we developed, that's just like something that has been historically done in FRC for gearboxes. And if it works for like cheesy goose, like it works for me. And now we have our victories.
Now, did you add 3-valve for the gear that went on the motor as well?
Yeah, so I added it for everything.
Okay.
So this is our first stage, right? So from the pinion to this gear is our first stage, and then we have a second stage going from this to this. then so we can add a sprocket here. So like again, imagine this is for an elevator or something. This chain can be used to drive our elevator up and down. So now we can just start defining where we want our gears to be. So this should be in the same place as that. So we're going to make a coincidence. And we can, I guess, make this gear at least. This. Actually, we're missing a bearing here, so we can pull that in from the design library. So we're going to use the same shaft retention method. So if we face the bearings inwards towards each other, then we can just use the shoulder of the hex to keep the shaft locked in place. So we can use copy with mates again if we wanted to. So with copy and mates, it saves all your mates and you just click where you want it. And it's super easy to do. And then we can, I guess for this, we can make this to this gear. And then with this gear, like, this is something I changed from like when I first guided it. When I first guided it, I actually had it up here, but because we're cutting, we can see if this clears everything, and the mounting screw for this motor actually interferes with it. So it's super easy to change, just dimension the gear with some spacing away from this bearing, and then it fixes the clearance issue. So that's why, like, this is a simple issue to fix, but if it required a redesign, then having your sketch for this plate allows you to really quickly change your bearing spacing and like change your gear ratio. So I'm gonna make this. And then an eighth of an inch sounds good. I can make this with this. So that's the main part of the gearbox done. So now all we have to do is we have to add the shafts, we have to add the standoffs, and then if you're really detailed, you can add all the mounting screws. So now I'm going to show you how, I guess, to cat this shaft. So we can measure here to here to know how long the shaft needs to be. And 1.121. Doesn't need to be that precise, we can do 1.12. So we make a new part. And this is going to look weird at first, but it makes it nice to change the shaft later on. Then you draw an infinite length line there. And then, so basically, we're going to turn down the two ends of the shaft, right? So we can kind of show that in here by drawing kind of like this type of shape. And closing it off. Making this vertical. And just to keep the part centered, we can select the midpoint of that line and then put it vertical to the origin. Then we're gonna just make the shaft symmetrical by, I guess, setting things individually. And then we want this round to be ½ inch, right? So we're just set at 0.5. And then, so this is the round that's gonna go into the bearing. And then we can just set it to like, I believe 3/8 works. This doesn't really need to be a specific length, it just needs to fit in the bearing. And then we said 1.12 for this. And if we select this. So this is the weird part. So just set this to like any I guess height. Oh, also when you dimension over a center line in the SolidWorks, it multiplies your dimension by 2 just because it thinks you're going to revolve. So that's an important thing to know. So we're going to revolve this. We have it. So this is obviously not the shaft we want to drive that gear, but if we go here and then we make this a hex, then we can make this co-radial to this. And what this does is it ties this entire shaft back to the first sketch. So if we make this horizontal, and then we can do up to surface, and then select this surface. So now if we go back to our first sketch, we bring this down to 0.5. You have to add 1 thou. It doesn't really matter, but it's just a glitch of SolidWorks. So now that's our shaft.
Will you do the retaining ring spacing there, or will you?
So we don't need to use a retaining ring, right? Because basically, if you have bearings on these rounds, it can't shift back and forth because you see this can't fit through the round bearing. So this is a nice way to avoid lock collars because those tend to not work. And then this is just a small detail. You can chamfer these just to make it easier to put into the bearing. So now we can insert this component back in. That's our shaft. We can make this concentric to this bearing. And then here's another nice feature of SolidWorks. There's an advanced mode called width. And then if you select the 2 sides of your axle or your shaft, and then your 2 sides